respiratory mechanics, or how the body moves air to keep the air in the alveoli the way it needs to be. All right, so today mostly what we're going to talk about is what's called gas transport. Or now that we've got that oxygen into the alveoli and the carbon dioxide out, well, how do things then move from the lungs to the body and back again? All right, so first we have to deal with this concept of partial pressure. So typically when we talk about a concentration, we talk about the number of molecules per unit volume. So like moles per liter, or the mass, so milligrams per liter, grams per liter, so on. Well, partial pressure is another way of describing concentration. And it's geared towards the concentration of a gas. So a gas can exist, like in the air around us, but gas molecules can also be carried in liquids. The blood in the end is going to carry the oxygen and carbon dioxide from the air in the alveoli out to the body where it can be used or removed. So to understand how that oxygen and carbon dioxide is moving, we have to understand this partial pressure. Okay, so let's take an example. We're going to talk about air. So air is a mixture of gases. We all learned that it's somewhere along the line. It's nitrogen, oxygen, and then a small amount of everything else, right? Or little bits of other things. Well, all that air together has a pressure. It pushes down on us all the time because the planet's gravity is pulling the air, down. So all of the air together, we have a pressure of 1 atmosphere, or 760 millimeters of mercury. So that's how much the air is pushing down all the time. And since that air is actually a mixture of multiple things, we can look at the relative concentration of nitrogen and oxygen by looking at the various pressures that they create. Because the ideal gas laws tell us that every molecule contributes to pressure equally, right? So we can just look at the number, or we can look at the ratio of molecules to see where this pressure comes from. An example is, I think, the best approach. All right, so if air is 78.6% nitrogen, 20.9% oxygen, right? That we can measure. So what is it? What are the partial pressures? Well, a partial pressure is the amount of pressure exerted by one gas in a mixture. So like we can look at the pressure that nitrogen makes, and we can look at the pressure that oxygen makes. And each one of those would be a partial pressure. So for example, the partial pressure of nitrogen, we take nitrogen at 78.6%, we multiply that by 760, the total, right? And we get the pressure contributed by nitrogen. So that's 597 millimeters of mercury. The numbers are not important here, it's the idea. So this is the partial pressure of nitrogen, the amount of the total pressure that is being created by just the nitrogen part of this mixture. All right, so we never talk about nitrogen in the body, but we do talk about oxygen. So we're going to see that oxygen has a partial pressure and carbon dioxide has a partial pressure. The key to understanding what that means is that it's simply a measure of concentration. So just like we might say there's 100 milligrams of sodium in this liter of water, partial pressure is saying the same thing. The higher the number, the greater the concentration. The lower the number, the less the concentration. And since diffusion is movement down a concentration gradient, substances will move from areas of high partial pressure to areas of low partial pressure, right? And we'll see that with oxygen and carbon dioxide. Okay, so once we understand that, now we know the language, right? We can talk about the concentration or amount of oxygen and CO2 in one place or another by using this partial pressure number. So very often that is expressed like this. So we'll have a P and an O2, a P and a CO2. So this is the partial pressure of oxygen. oxygen concentration, in other words, and this is the partial pressure of CO2, or CO2 concentration. All right. So if we look at movement of oxygen and carbon dioxide around the body, we can simplify it way down. All right. So here's our cross that we saw in the cardiovascular system, the two circuits of the cardiovascular system. The systemic circuit carrying blood to the body, to the tissues, and then we have the pulmonary circuit going across, carrying blood out to the lungs and back. And what we can see is, if we zoom into two spots, we can see gas exchange, or the movement of oxygen and carbon dioxide from the blood somewhere else and from somewhere else back into the blood. All right, so first up here is at the lungs. So at the lungs, we have the case where blood is coming very close to air. And as long as ventilation is adequate, in other words, as long as we're breathing enough, the air in the alveoli, okay, so this is blood in the capillaries in the lungs, right? So this whole top box is in the lungs, right here. So here's blood, here's air in the alveoli. So that air has a high pressure, or a high partial pressure of oxygen, right? So a high concentration of O2, and a relatively low concentration of CO2. Now that number, PCO2 of 40, that is much higher than what you'd find in the air around us, right? But the air in the alveoli is never completely replaced, because they never empty. So the CO2 level in the alveolus, even in the normal, healthy person breathing adequately, is usually quite a bit higher than what you find in the atmosphere. All right, so that's the air in the alveolus, 140. Well, the air or the blood in these capillaries is going to change as it goes by this alveolus. That's sort of the whole point of having lungs. So what enters the lungs from the heart is deoxygenated blood, right? Blue blood, we've all learned it that way. Well, if we look at the characteristics of this blood entering the lungs, we see the PO2 is 40 and the PCO2 is 45. So we have a very low oxygen, we have a very high CO2. That's just what you'd expect. This is blood coming from the tissues. The oxygen has been removed, and CO2 has been added as the tissues have done their metabolism. All right, so now we come very close to air. So remember that respiratory membrane we talked about last time? Very thin, just two very thin cells with a very thin sheet in between. Well, that's this spot right here. And as blood comes to that space, oxygen and carbon dioxide can move. And they're going to move down their concentration gradient. All right, so here we have a PO2 of 100, a PO2 of 40. Well, 100 is greater than 40, so oxygen is going to move into the blood, down towards the smaller number, down the concentration gradient. So that's here. CO2, we have a CO2 of 45 coming in and 40 in the alveolus. So it's the opposite direction. The CO2 is going to move towards the lower number. So it's going to move out of the blood and into the air. So then what leaves the lungs after it's passed that respiratory membrane and the alveoli, the blood in the capillaries has the same partial pressures as what we find in the alveoli, right? So an oxygen of 100 and a CO2 of 40. So a high oxygen level, a relatively low CO2 level. See, the CO2 levels are not very different from each other. So even though 40 and 45 are not very different, it's enough to cause motion. Things will always move towards the lower partial pressure, so to speak. So blood leaving the lungs has the same oxygen and CO2 makeup as the air in the alveoli. So high oxygen, low CO2. All right, so boom, it goes back to the heart. Now it's going to go out into the systemic circulation. So arriving at the tissues now, and this is any tissue, skeletal muscle tissue, skin, bone, liver, kidney, anything but the lungs. Now what does the blood look like? Well, the PO2 is 95 and the PCO2 is 40. So the CO2 hasn't changed in the journey, so to speak. because we came from here, went through the heart, now we're here, let's say. Well, the oxygen is a little different, and that's because as blood moves through the body, it is always giving up a little oxygen. So the longer its journey, the lower the oxygen level will be when it finally arrives. But if we look at the tissues, the oxygen level in the tissues, the PO2 of the tissues, is very low, 40, and the PCO2 is high, 45. So 95 is greater than 40, and we know that oxygen is always going to flow towards the lower number, right? So oxygen is going to move out of the blood at the tissues, and CO2 is going to move in because we have a CO2 of 40 in the blood, 45 in the tissues, so CO2 is going to move in. So by the time blood leaves the tissues, the PO2 is 40 and the PCO2 is 45, just like it is in the tissues all the time. So now this blood is going to go back to the lungs to pick up oxygen, and here it is again. So the same metrics, PO2 of 40, PCO2 of 45, just like we talked about the blood coming in to the lungs in the first place. So by looking at these two spots, an area of lung and an area of tissue, we can see what we call gas exchange, or the movement of oxygen into the blood and then into the tissues, and then the movement of CO2 out of the tissues and then back into the lungs where it can be exhaled. All right? So this whole system functions because the air in the alveoli is kept at these numbers. If we were to stop breathing, the air in the alveoli, the oxygen level would go down, the PCO2 level would go up, and this motion of oxygen and carbon dioxide would stop, or at some point even reverse, so that, in other words, that would be respiratory failure, is when the air in the alveolus is so different from, or similar enough to the air in the blood that nothing moves. So the reason why we ventilate or move air is to keep these numbers correct. All right, so this is the concept of gas exchange. All right, yes?
Do you have a homework question about where is the greatest partial pressure for carbon dioxide?
So what do you think?
I feel like I'm spinning right now on that last slide.
Okay. Well,
I'm guessing the 45.
yes. So the whole system evolved to get carbon dioxide out of the tissues. So if it's always going from high to low, that would mean the tissues would have to be the highest and the lungs would have to be the lowest. So that CO2 is going to load, it's going to move down.
Is that an expired air then?
In expired air, what are the other choices?
Venous blood, alveolar air, expired air, inspired air, and arterial blood.
It would be, well, it would be highest in venous blood.
Okay.
Yeah, because it isn't expired air, even though that you might think that way.
Yeah.
And that's because every time you breathe out, the air in your alveoli is mixed with the air that's in your, like your trachea and your bronchi. So the CO2 concentration actually falls because the air in those spaces has a lower CO2. Tricky question, but venous blood is of those, yeah. Or the tissues themselves have the highest, but you're looking for the lowest.
No, it's the greatest partial pressure.
Of CO2?
Mm-hmm.
Yeah, is there an option for the tissues?
No.
Then venous blood, your next best.
Okay.
Because if you look here, this is venous blood. So this is blood coming back to the heart right here,
Yeah.
right? And it matches what's in the tissues.
Okay.
So they're the same. Good question. Yeah, the key to this whole slide, even though it's complicated, is everything is always moving down its pressure gradient. So from high numbers to low numbers. If you remember high numbers to low numbers, and then remember the numbers, then you know where things are moving in the blood. All right. Okay, so oxygen gets into the blood, carbon dioxide has to get out. But we have another issue, and that is the blood, which is mostly water. Water doesn't carry oxygen very well. In other words, if you bubble oxygen through the water, most of that oxygen comes right out the top. In other words, the water can't hold on to it. But the cells of our body need huge amounts of oxygen because there are so many of them. There's trillions of cells, and they're very busy, little things, so they need tons of oxygen, far, far more than what the blood could carry, in the water of it. So enter our friend hemoglobin, which we introduced when we talked about red blood cells. So hemoglobin's job is to carry oxygen from the lungs out to the tissues. And it does that using an iron ion in a heme ring, like we talked about in the last unit. And each one of these heme with their iron can hold on to one O2 molecule. So not an oxygen atom, but an oxygen molecule, O2, just like it's found in the air. So because there are 4 of those in each hemoglobin molecule, each hemoglobin can carry 4 molecules of oxygen. So it is a very efficient carrier. And we have huge amounts of hemoglobin, not in the blood, but in the red blood cells. So inside the red blood cells, that's where the oxygen is going to be carried principally. All right. So in order to understand what hemoglobin is doing or why it's important, we have this concept of oxygen saturation or hemoglobin saturation. And 20 years ago, nobody heard about this, but today, because of a machine called a pulse oximeter, many of us have heard the term SATs or oxygen saturation. Now, every time you go to the doctor, they put that red thing on your finger, right? And you see the little 97% or whatever. Well, what that device is measuring is how much oxygen is being carried by the hemoglobin molecules in your red blood cells. So it's a simple ratio. So at 100%, that's the easiest one to understand. All of the hemoglobin molecules are completely full of oxygen. So all of the hemoglobin has 4 oxygen molecules attached. Now, in the normal, healthy human being, you're never at 100%. The body didn't evolve like that. So chances are, if you see 100%, you're either, maybe agitated and you're breathing a little more than you need to, or the patient is on a little supplemental oxygen. So, but that's what it means, is all of those binding sites are occupied. So what does 95% mean then? It means 95% of the possible hemoglobin binding sites have oxygen attached. And we can measure this with that little red light because hemoglobin changes color as it loses oxygen. So the more oxygen a hemoglobin molecule has, the redder it is. And the less oxygen it has, the bluer it is. So when we look at our veins and we see this kind of blue hue to them, it's because hemoglobin literally changes its color. And that's what that little device measures, is the color of the hemoglobin that's circulating past it. All right, so oxygen saturation. Okay. So we can take this concept of saturation, okay, so that's over here. So 100% saturated, 10%, 0% saturated. And we can put it next to the partial pressure of oxygen in various places, and we can see why hemoglobin is a good oxygen carrier. All right, so what do you need for a carrier? A carrier needs to pick something up in a place where there's lots of it, right? And then it needs to deliver it or drop it off where it's needed or where there isn't much of a thing. And hemoglobin evolved to do just that, which is sort of a neat trick. And that is, okay, so this is the partial pressure of oxygen. In the lungs, the PO2 is like 100, right? We saw that in the previous slide. So when the oxygen levels around hemoglobin are high, it grabs hemoglobin very easily. In other words, its saturation goes up. The number of binding sites occupied go up and up and up. So in the lungs, hemoglobin grabs hold of oxygen very easily. But, that's only part of it. We want hemoglobin then to let go of that oxygen where it's needed. And it does that because as the PO2 decreases, so like here's the lungs, here's the tissues, right? 40 is the PO2 in the tissues. We see at 40, the oxygen saturation is like 75%, 25% less than it was in the lungs. So that difference is oxygen that hemoglobin has released. or let go. So hemoglobin picks up oxygen where there's lots of oxygen, and it delivers or drops oxygen, dissociates is what that's called, but lets go of it where the oxygen concentration is very low. So let's say you have a hard-working skeletal muscle, and it's burning up oxygen very fast. Well, its PO2 might be 20 or even lower than that. So when hemoglobin reaches that neighborhood where the oxygen or where the muscle is hard-working, now its saturation is 20%. So in other words, it's going to drop almost all of its oxygen in those places where it's needed most, where oxygen levels are very low. Hemoglobin is going to dump extra oxygen so that it can solve that problem. So this curve, which is called the hemoglobin dissociation curve, and you may see it in future classes because it's sort of a famous and typical way of talking about hemoglobin. But all this curve is showing you is that hemoglobin is a good carrier of oxygen. It picks it up when oxygen levels are high, and it drops it off when oxygen levels are low. All right? Okay, so your book talks a lot more about it than that, but that's the general idea. All right. And it doesn't end there. The hemoglobin is a highly evolved molecule that does us a world of good. And this is another example. Any tissue that is busy is going to become more acidic because our cells have a tendency to make acid as they work, particularly as they work hard. So a busy tissue is an acidic tissue, and a busy tissue needs oxygen, right? Because the more active a tissue is or a cell is, the more oxygen it's going to need. Well, the hemoglobin saturation curve changes according to pH. So essentially, it goes like this. As the pH goes down, in other words, as the tissue becomes more busy, the hemoglobin delivers more oxygen in that region. Okay? So we have this pH effect. We have the same thing with temperature, that the warmer the tissue, the more oxygen it needs. So the further down, the further towards the right that this oxygen saturation curve moves, the more efficiently hemoglobin delivers oxygen in those areas. So I know that not many people are sort of graph-minded or algebra-minded here. So the take-home message is, as tissues become more acidic, hemoglobin saturation goes down. In other words, hemoglobin releases more oxygen in acidic tissues and in warmer tissues. Okay, and that, believe it or not, that is represented by these colored curves from your book, but I don't think it's very intuitive to most of us non-mathematicians. All right. Okay, so let's try the new Socrative thing and see how terrible it is. Okay, so pulmonary ventilation refers to which of those things? Huh? The app doesn't work. Are you in the app or the web?
The app doesn't work?
I think the app doesn't work. Try the web version if you can. It's m.socrative.com, and then you click student login. I don't think this is permanent. I think the app will come back. But it doesn't work on my device either. Is anybody getting anything?
It's supposed to be up in a few hours.
Oh, they took it back down?
Yeah.
All right. Well, we'll wing it. Okay, so what is pulmonary ventilation? Well, ventilation ultimately is the movement of air in and out of the lungs. So that's going to be C. All right, because A, movement of dissolved gases, that's what we were just talking about. That's gas exchange. Oxygen and CO2 moving across the capillary wall, or the capillary barrier. Utilization of oxygen, technically that's respiration, and it's internal respiration or cellular respiration. Movement of dissolved gases from alveoli to blood, that's, again, gas exchange. So D, E, and A are all gas exchange. All right. At a PO2 of 70 and normal temperature and pH, hemoglobin is what % saturated? Right? So that's that saturation curve. It looks like this. And over here, this is a PO2 of 100, PO2. And, this right here is about a PO2 of 40. You can remember that the shoulder or the slope of the curve is steepest at 40. So where would 70 be? Well, it would be about here. So of our choices, is it A 75, which would be here, B 25 here, C 10, D 50. So you're down to, it has to be E. So more than 90.
I'm so lost on
On what?
this whole, the chart, everything we've gone over today pretty much.
Okay.
Blur.
It's dense, but there's not very many concepts. Here, we'll go. Okay, so the main concept here is oxygen and carbon dioxide have to move, right? And they move down their pressure gradients.
Yes.
Okay? So from 100 to 40, and then from 45 to 40. So that way. So
Always moving towards the lower number.
yes, they're always moving towards the lower number. So that gets the oxygen and carbon dioxide into the blood, right?
Yes.
And then the heart's going to pump it around, and then at the tissues, the environment of the tissues is opposite of the alveoli. So we have a low PO2 and a high PCO2. Here we have a high PO2, a low PCO2. So carbon dioxide flows in here and flows out here, always down its gradient from high to low, because this is what's coming in. So from high to low, and then from high to low. So that's CO2. And then oxygen, we go from high to low, and then high to low again. Does that sort of make sense?
It does, but then on that question, I had no clue how to answer it. I didn't understand on the PO240 and the P100. I don't understand any of that.
Okay, what part of it don't you understand?
Can you go back to the question, just like
Yeah, which question?
the one where you drew the shoulder and that one?
Okay, that's I went too far back then. All right, so this is how the molecules are moving. This curve is all about hemoglobin. So the oxygen gets into the blood down its concentration gradient, and then hemoglobin snatches it up.
Yes.
So on that question, what we were looking at is it said at a PO2 of 70 or 75, what is the oxygen saturation? So
Okay. I'm sorry.
yeah, do you get it?
Yeah, I do
Okay.
now.
Okay.
It's reading a graph, basically.
Yes, yes.
Okay. I was
The
thinking-
tricky bit, and the reason when you look for the text on some of these, the tricky part is what the graph means. We can all read a graph, but what this is the unique character of hemoglobin, because it means that where there's lots of oxygen around, it wants to grab hold, it wants to be full.
Yes.
And when there's little oxygen around, it wants to be more and more empty. So what that means is just like a truck, it pulls into the lungs and it loads up with oxygen. But as the truck goes out, the truck gets smaller, so oxygen is spilling out all the time. Does that sort of make sense?
Yes.
Yeah.
I guess I didn't realize you were looking at the graph. I was thinking it
You were
was
looking at
another chart.
Okay. No, that's all right. That's what we're here for. Okay. So that's oxygen transport. Hemoglobin is the star of that story, right? Well, we also have to move carbon dioxide around. And unfortunately, it isn't as simple as moving oxygen around. We don't have a hemoglobin molecule for carbon dioxide. So CO2 is produced in all the cells, right? It moves into the capillaries of the venous blood by diffusion, but then it has to get back to the lungs. All right. So just like with oxygen, the water of the blood can't carry all of the CO2 that's manufactured by the body. So we have to have some other systems. And in the case of CO2, we have 3 systems. So of the 100%, 7% is as PCO2. Okay, so that's this one at the top. So 7% of all the oxygen, or all the CO2 that's transported is simply dissolved in the water of the plasma. Because we know, we drink soda pop, right? Soda pop is essentially CO2 dissolved in water, okay? So water can carry some CO2, but 7% isn't going to cut it. So now we have, what do we do with the rest? Okay, so the remaining 93% enters red blood cells. Same place the oxygen came from, right? So of that 93%, 23% of that is carried by hemoglobin. So hemoglobin is a super cool molecule because not only does it carry oxygen around, but it also carries carbon dioxide back to the lungs as well. So that's 23% is bound to hemoglobin. So 23%. And I do want you to know these numbers here is as HB. HB is hemoglobin, right? So HB CO2. So that leaves us with 70%. Okay? That 70% is carried back to the lungs as bicarbonate. All right, so this equation, I'm just going to write it over here, is one that we are now going to see in the course multiple different times. All right? It's an equilibrium, which means that it's a reaction that can go in either direction according to the circumstances. Okay. And to give you a name, this molecule right here is bicarbonate, right? And this molecule right here, its name is carbonic acid. The others you should know, right? H2O, CO2, H+, that's just a proton. Okay, so this equation can be pushed in either direction. So it can be pushed this way, where bicarbonate and H pluses are put together to make carbonic acid, which then splits apart and makes water and carbon dioxide. All right? It can also be pushed this way. We can take CO2 and water and kind of jam them together, and they make carbonic acid. And carbonic acid is unstable, so you don't find much of this in the blood ever, because it's either going to fall apart this way or it's going to fall apart this way. But it is the intermediate step. So CO2 plus water, we get carbonic acid, but then we're dissolved in water, so that carbonic acid breaks apart into H plus and bicarbonate. So 70% of the CO2 that's manufactured by the body, in the tissues, this equation moves towards the left, right? CO2 becomes bicarbonate. Because, where did the carbon go? Follow the carbon. Boom, boom, boom. So this CO2 can be made into bicarbonate, right? So in the tissues, that's what happens. But then when you get to the lungs, it goes the other direction. So it means that the CO2 that's produced by the tissues can be carried as bicarbonate and then returned at the lungs to CO2, so it can then be blown out into the atmosphere, right? So 70% of the CO2 made follows that carbonic anhydrous system. Okay, so CO2 goes into the red blood cell. It's transformed into carbonic acid, so that first step. That carbonic acid dissociates, and the H plus and bicarbonate go in two different directions. The H plus goes and is bound to hemoglobin, so hemoglobin is going to carry that excess proton, and then the bicarbonate is shuttled out of the red blood cell and into the plasma. Now, in the lungs, this whole process reverses. Bicarbonate is shuttled in, H plus is added to it, that makes H2O and CO2, and then CO2 diffuses into the lungs. So it sort of goes backwards. All right, which you can sort of see in this picture. This is one of my favorite pictures from your book. It's been in lots of other books too. It's very dense, but it's one of those, if you get what you're looking at, it's a good sort of test, then you have a good concept of gas transport, or how are CO2 and oxygen moved around. Okay, so top one is oxygen. Here's the alveolus, here's the blood. So oxygen in the alveolus moves into the blood, down its concentration gradient, right? A tiny little bit of that oxygen stays dissolved in the water of the plasma. But the vast majority, the big arrow, gets joined to hemoglobin, so we have hemoglobin carrying oxygen, right? Now, we leave the lungs and we arrive at the tissues. So here's lungs, here's tissues. Now everything goes in reverse, right? The oxygen is released from hemoglobin because its saturation curve, it's now at a different PO2, so that it's dumping oxygen. The oxygen enters the tissues, right? And gets used up by the cells. So in return, the cells produce carbon dioxide and energy as well, but the carbon dioxide diffuses out of the cells into the blood, again, down the concentration gradient. 7% just stays as CO2 dissolved in the plasma, right? So that's this bit. 23%, that's this bit, is bound to hemoglobin. So hemoglobin is going to carry it back to the lungs. And then 70% uses that carbonic acid equation or system, where the CO2 is added, is crammed together with a water molecule to make carbonic acid, which breaks apart into bicarb and a hydrogen ion. The hydrogen ion gets clung to a hemoglobin, and the bicarb gets shifted out. Now, why is it shifted out? Because otherwise, if the bicarbonate level inside the red blood cell got too high, that equation would start to reverse. So the bicarbonate has to be thrown somewhere else. And it is. It's shifted out of the red blood cell and into the plasma so that more and more bicarbonate can be made. So it's kind of like a machine like that. If the red blood cell didn't evict the bicarb, that whole system would start to back up, like a bad plumbing problem. All right, so now we have our carrying states. CO2 is bound to hemoglobin, bicarbonate is in the plasma, CO2 is in the plasma. So now we're going to circulate and we're going to come back to the lungs. Now everything that we just did gets reversed. So the CO2 in the plasma enters the alveolus, so it can be exhaled. The CO2 bound to hemoglobin, the CO2 is released, and that CO2 enters the alveolus where it can be exhaled. And then that equation over on the side there reverses. So the bicarbonate is brought in, the hydrogen ion is added to it, made into carbonic acid, which breaks down into CO2 and water. The CO2 is diffuses into the alveolus and then is breathed out, so it's exhaled. So this is gas transport in one slide. So the oxygen piece and the carbon dioxide piece. And we're going to look at that equation again when we look at the kidney and when we look at the acid and base balance of the body. So it's one to, have it somewhere in your notes so that you're familiar with it, because we're going to talk about it more than just this one. All right. So the lungs are very often compared to a balloon. And that's because in many ways they're very balloon-like. In other words, it takes effort or energy to inflate the lungs, but it doesn't take any energy to deflate them. They deflate themselves. So there are two concepts that sort of go along that direction, and that's compliance and resistance. So in disease states of the lungs, these two factors change. So it's important to know what they are. So compliance is how easily the lungs are inflatable. How floppy the balloon is one way to put it. If you've got a balloon, you've blown it up a bunch of times, the 10th time you blow it up, it's much, much easier to blow up than the first time, right? So that is an increase in compliance. The balloon has become more compliant, easier to inflate, easier to work with. So that's one bit. Compliance changes in disease states for a variety of reasons. Anything that increases that respiratory membrane space will decrease compliance. like a premature baby, for example, that doesn't have surfactant, their compliance is very low. So what this all means is any time you have to put extra effort into inflating the lungs, that means they have a compliance problem. All right? So that's compliance, how stiff the lung is. And then resistance is how smoothly air flows through the lungs. So, we talked a little bit about asthma last time, and asthma is a problem with resistance. The lungs are compliant, but the nozzle of the balloon has become so small that it's very hard to inflate it. So resistance is affected by bronchoconstriction, like asthma, as well as anything else that affects the tubes of the lungs. So compliance and resistance are just two characteristics of the lung that change with respiratory disease, which you'll learn more about in other classes. All right. Okay, so your book goes into a lot of detail, I think, about the control of respiration by the brain. And it's far more detailed than I'm interested in you knowing, because this stuff doesn't come up clinically very often. These other things we've been talking about do. So I'm going to limit it what you need to know. I want you to know the DRG and the VRG. So the dorsal respiratory group and the ventral respiratory group are the principal controllers of respiration. So you know that unlike the heart beats itself, right? The respiratory system doesn't have that. There isn't a pacemaker built in. So the brain has to tell the diaphragm and the intercostal muscles to contract in order to breathe. It's one of the big differences between respiration and the cardiovascular system. Is the cardiovascular system is sort of automatic. That heart's going to keep beating whether there's a brain in your head or not. The respiratory system, not the case. If your brain is totally dead or damaged, you won't breathe because there won't be a signal to contract the diaphragm and make that happen. So the DRG and the VRG are found in the medulla oblongata, and they are the primary pacemaker or rhythm setter for the respiratory system. And then, we all know that we can do all kinds of things with our respiratory systems, right? We can play instruments, we can sing, we can whistle, we can do all kinds of stuff. And, we can do things like breathe. We're sitting down to a meal and we're eating. Well, we have breathing during that time too, right? So there has to be a way to coordinate, breathing with eating and eating with talking and all those things. So there are multiple levels of control over the respiratory tract. So the DRG and the VRG are sort of the basics, right? That's going to control things that we never think about. Like increasing our rate of breathing when we exercise. We don't do that on purpose, right? But the DRG and VRG do that for us. Okay. Up here, a little higher in the brain, in the pons, we have the apneustic centers and pneumotaxic centers. These modify what the DRG and VRG do in order to coordinate respiration with other things. All right, so that's those guys, the coordination and smoothing of respiration. And then the cerebral cortex can take control of the respiratory system itself, which is what is happening like right now for me. My cerebral cortex is controlling my respiratory tract as I'm talking. Same with playing an instrument, whistling, those kinds of things. Now, the interesting thing is, even though the cerebral cortex can do the fanciest stuff, in the end, it doesn't have the final say, because as your physiology changes, in other words, the classic example is holding your breath. Can you kill yourself by holding your breath? No, you can't. Because at some point, the cerebral cortex, which is holding the breath, is overridden by the DRG or the VRG, particularly when things like oxygen levels get too low or CO2 levels get too high. You can't override the cerebral cortex's control. So, no, you cannot kill yourself by holding your breath. Your medulla oblongata is going to override those higher centers at some point. All right. So way too much information on some of these. There are two kinds of breathing, quiet breathing and forced breathing. And your book's point here was how the dorsal and respiratory ventral groups differ in what they do. But I just want you to know that there are, quiet breathing is this: active inhalation, passive exhalation, right? Because the lungs will deflate themselves. So like what you guys are doing right now is quiet breathing. The diaphragm is contracting and the intercostals are contracting to breathe in, but then when you breathe out, that's just the lungs and the chest wall sort of collapsing back in on themselves like they normally do. So that's quiet breathing. In forced breathing, both the inhale and the exhale are powered, okay? And they're powered by those accessory muscles that we talked about on Monday or last Friday. So forced breathing, active inhalation, active exhalation, and use of the accessory muscles. Quiet breathing, active inhalation, passive exhalation. So quiet breathing, forced breathing. You don't need to know the DRG and the VRG and all that stuff, or what they do like this. All right. So this I stick in at the end because it is a common misconception that I hope you leave my class, being smarter for. And that is, we're all taught in grade school, or maybe it's an instinctual understanding, I don't know. But we think that we breathe to get oxygen into our bodies, right? And in a sense, of course we do. We need oxygen. But, we breathe, 15 to 25 times a minute. So why that fast? It isn't about the oxygen, because the truth is there's plenty of oxygen in the air, and the difference of oxygen level between air and tissues is great enough. Oxygen moves around our bodies very easily. So it's really all about CO2. It is the CO2 concentration that determines how deeply we breathe, how often we breathe, and in many ways, it's the limiting factor. Could you make a human that was 10 times larger than us? And no, you couldn't, because they wouldn't be able to get rid of the CO2 that they make. They could probably still oxygenate, in other words, get enough oxygen, but they couldn't get enough, they wouldn't be able to get rid of all their CO2 production. So, the lay person out there says, it's oxygen, that's why we breathe. And I want you to know that no, principally we breathe to get rid of all that CO2 that we make. And we'll see that idea come up when we talk about the acid-base balance of the body, that the sort of the thinnest ice physiologically is in our CO2 management. So if you have a patient who's, they've got something lodged in their trachea, let's say. So Heimlich maneuver fails, you've got respiratory failure. What they're going to die of is increasing CO2 levels, because that is tolerated much less well. In other words, we don't tolerate high CO2 levels as well as we tolerate low oxygen levels. Because people climb Mount Everest without supplemental oxygen sometimes, and they're breathing oxygen, 10, 12%. So we can do plenty even at a lower oxygen level, but CO2, that's what we have trouble managing or getting rid of. So a little lesson in that. All right. So just like everything else in the body, respiration is controlled. And just like my big long speech there, you can see that it's arterial PCO2 is the key factor in regulating respiration. When CO2 goes up, breathing goes up. We breathe faster, we breathe deeper. As we breathe faster and deeper, CO2 is eliminated more rapidly. As CO2 is eliminated more rapidly, we come back to a normal PCO2. The opposite is also true. If the PCO2 gets too low, that's called hypocapnia, then respiration is reduced. Now, this doesn't happen very often because we are CO2 factories. We're always producing carbon dioxide. But if you breathe too fast on purpose, so like hyperventilation, or you're anxious, so you're breathing fast, then your CO2 will fall, and eventually your respiratory drive is slowed down until the CO2 comes back up to normal. And just as our parting point, Navy SEALs and snorkelers take advantage of this by they'll breathe in and out a lot for a few minutes before they go on a deep dive or on a long a long dive, because if you blow out the CO2 in advance, you can hold your breath longer. All right, so that is it for today. We'll talk a little maybe about respiratory reflexes next time, although I don't think so. All right, so enjoy your fall break, everybody.